Hi students, I am Prashant B. Chandran, Assistant Professor Automobile Engineering Department, SN8 Adur. Okay, today I am going to teach you about another problem in LMTD method. This problem number 2. Okay, let us start the problem. Is air at 120 degrees centigrade is cooled to 50 degrees centigrade by passing through the counterflow heat exchanger tubes of 12 mm internal diameter surrounded by water, which enters the cooler at 10 degrees centigrade and leaves at 25 degrees centigrade. Find the LMTD. That is, here air is cooled from 120 degrees centigrade to 50 degrees centigrade. That is, air is the hot fluid. By passing through a counterflow heat exchanger, it is given that the type of heat exchanger is a counterflow heat exchanger, and the diameter of the tube is given as 12 mm, that is 12 into 10 raised to minus 3 meter, surrounded by water, which enters the cooler at 10 degrees centigrade and leaves at 25 degrees centigrade. That means water is the cold fluid. First of all, we have to find out the LMTD. Okay, and second part of the question is, if the air velocity in the tube is limited to 6 meter per second, that is, velocity of air is given as 6 meter per second, then find the length of the tube required. The question is to find out the length of the tube L. It is given that tube inside heat transfer coefficient, that is HI, is given as 65 watt per meter square Kelvin, and tube water side heat transfer coefficient is 200 watt per meter square Kelvin, that is HO is given as 200 watt per meter square Kelvin. Then density of air is given as 2.85 kilogram per meter cube, and for air Cp is given as 1.005 kilojoule per kilogram Kelvin. Okay, this is the question. That is, from the question itself, it is clear that air is cooled from 120 to 50 degrees, that is, air is the hot fluid and it is the counterflow heat exchanger. The diameter of the tube is given as 12 mm and surrounded by water, which enters the cooler at 10 degree and leaves at 25 degree. That is, water is the cold fluid. We have to find out the LMTD. That is, the velocity of air is given as 6 meter per second. We have to find out the length of the tube required. Okay, that is the question. The tube side heat transfer coefficient, that is HI is given as 65 watt per meter square Kelvin, and HO is given as 200 watt per meter square Kelvin. Density of air is 2.85, and Cp, supersedited constant pressure for air, is 1.005 kilojoule per kilogram Kelvin. This is the question, and we have to find out, first write the given data. It is given that it is a counterflow heat exchanger. Hot fluid is air. The inlet temperature of hot fluid air is T1 is 120 degrees centigrade and capital T2 is 50 degrees centigrade. Considering the cold fluid, that is water, inlet temperature small T1 is 10 degrees centigrade and outlet temperature of cold water small T2 is 25 degrees centigrade, and the other given data are diameter of the tube is given as 12 mm, that is 12 into 10 raised to minus 3 meter, or 0.012 meter. Okay, and then air velocity V is given as 6 meter per second. Then the inside heat transfer coefficient of the tube is given as HI is equal to 65 watt per meter square Kelvin, and outside heat transfer coefficient HO is given as 200 watt per meter square Kelvin. Okay, then density of air, that is rho, is given as 2.85 kilogram per meter cube. Then Cp, supersedited constant pressure for air, is given as 1.005 kilojoule per kilogram Kelvin. These are all the given datas. Then define, that is we have to find two values, that is first of all LMTD, it is logarithmic mean temperature difference, and second part of the question is to find the length of the tube required, that is L. Then solution, that is first part, we have to find out the LMTD. For that we have to draw the temperature distribution diagram for counterflow heat exchanger, or counterflow heat exchanger. Okay. This is the first step. First of all, we are drawing the hot fluid, that is air, hot fluid air. Since it is a counterflow heat exchanger, the arrow for cold fluid should be given in the opposite direction, that is for water. Then temperature, inlet temperature of hot fluid T1, capital T1 is equal to 120 degrees centigrade, and the outlet temperature difference, temperature of hot fluid is capital T2 is 50 degrees centigrade, and the inlet temperature of cold fluid, that is water, small T1 is equal to 10 degrees centigrade, and small T2 outlet temperature of cold fluid is 25 degrees centigrade, and the left side heat temperature difference gives theta 1, and the right side temperature difference gives theta 2. That is theta 1 is equal to capital T1 minus small T2, which is equal to 120 minus 25, which is equal to, that is theta 1 is equal to 95 degrees centigrade. That is left side heat transfer temperature difference, theta 1 is equal to 95 degrees centigrade. Then theta 2 is, that is the right side temperature difference, that is capital T2 minus small t1, is equal to 50 minus 10, that is theta 2 is equal to 40 degrees centigrade. Okay. Next we have to find out LMTD. We know the formula for LMTD is LMTD is equal to theta 1 minus theta 2 the whole divided by ln of theta 1 divided by theta 2, substituting the values, that is 95 minus 40 divided by ln of 95 divided by 40, we get 63.58 degree. That is LMTD is equal to 63.58 degrees centigrade. This is the first part of the question. The second part is to find out the length of the tube required, that is capital L. So for as usual we have to find out the heat transfer Q. Q is equal to, you know the formula, m dot h into Cph into T1 minus T2, that is mass of hot fluid into temperature, specific heat of hot fluid into temperature difference of hot fluid. But here m dot h is not given, so we have to first find out the value for m dot h, and we know that m dot h is equal to, mass flow is given by the equation rho into A into V, where rho is the density, A is the area, that is cross-sectional area, and V is the velocity. Density is given as 2.85 over here, and the area A is equal to pi by 4 into d square. Diameter is given as 0.012 meter into square into velocity is given as 6 meter per second. Plus we get the m dot h is equal to 1.934 into 10 raised to minus 3 kilogram per second. That is the mass flow rate of hot fluid. We got the answer, and we have to substitute this value in equation, that is equation of Q. Okay. Q is, okay, I am explaining it once again. Q is equal to m dot h into Cph d1 minus d2. We get the value for, that is substituting this, we get Q is equal to 0.136 kilowatt. Also Q is equal to UA LMTD, and the area is equal to Q divided by U into LMTD. But U is not given, but HI and HO are given. HI and HO are given. The equation for overall heat transfer coefficient U is capital U is equal to, we know that the overall heat transfer coefficient U is equal to HI into HO divided by HI plus HO. That is 65 into 200 divided by 65 plus 200. We get the value for U is equal to 49.06 watt per meter square Kelvin. Watt per meter square Kelvin. This is the value for U. We have to substitute this value for U in the equation for Q. That is Q is equal to UA LMTD. Q is equal to UA LMTD. For area is equal to Q divided by U into LMTD. Area is equal to Q divided by U into LMTD. That is 0.136 into 1000. Because Q is in kilowatt, we have to change it into watt, because the U value is in watts, watt per meter square Kelvin. To compensate that, we have to change that Q also in watts. It is 0.136 kilowatt is equal to 0.136 into 1000 watts. Okay. We get the heat transfer, the area of heat exchanger as area is equal to 0.04362 meter square. We know that surface area of heat exchanger A is equal to pi dl. Surface area A is equal to pi dl. Therefore, L is equal to area divided by pi d. Pi d is equal to, substituting the values, we get 0.04362 divided by pi into diameter is 0.012. We get the value for L as L is equal to 1.157 meter. That is the length of the heat